Those are just some of the generalisations that are made about desert or dryland environments, but you only need to come to somewhere like here, the Sedilo Hills in the Kalahari Desert of northwest Botswana, to realise that the majority of those generalisations are completely misleading. Whilst deserts are defined by their lack of water, that moisture deficit can occur for a whole variety of reasons. So in this particular part of the Kalahari, rainfall levels aren't actually that dissimilar to areas of eastern UK, say East Anglia, but the key issue is that when rainfall does occur here, it tends to fall during the hottest months of the year, during the summer, so the majority of the moisture evaporates away fairly rapidly, hence the reason you get this kind of savanna landscape. There's been a tendency when doing research in desert or dryland environments to focus more on the exotic, things that are different to the kind of environments that maybe you're used to at home. So a lot of work in desert or dryland areas has tended to focus on things like the work of the wind, in how it shapes sand dunes, or perhaps some of the more unusual weathering phenomena that occur on rock surfaces in deserts. But it's really important that we don't overlook the significance of things like water. Water is absolutely fundamental for shaping desert landscapes through, for example, fluvial activity, the work of rivers. But it also is very important as an agent for cementing sediments, providing a source of moisture to bind sediments together and prevent them from being eroded. So it can act as both an erosional agent but also as a mechanism for preventing erosion. But that's enough from me. I could talk for hours, and it's starting to get a bit hot now as the sun rises, so I'm going to hand you over to someone who knows an awful lot more about desert environments than I do, Dave, who should be standing somewhere down there, finger poised over the mouse, ready to start his PowerPoint presentation and tell you a bit more about some of the work that he's done in desert regions, and particularly to emphasise the importance of water in these kinds of very, very fragile environments. So over to you, Dave.
Excellent. So everybody, thank you first of all to the Vice-Chancellor for that words of welcome. Thank you to everybody for coming along. It's really humbling to see so many friends here, colleagues here, people I've worked with for many years coming along to this event. So thank you all, and thank you, Dave. I've now started talking about myself in the third person, which is obviously something that happens when you get elevated to professor. But what I want to do this evening is to share with you this evening some of the research that I've undertaken over the last 20 or so years, looking at dryland, landscape change and climatic variability. I've had the fortune to work on a huge range of different projects with a variety of absolutely fantastic people, so it's not possible to give you a flavour of everything, but what I want to do is just to pick some examples of some of the work that I've done, and as Dave said, try to emphasise the importance of water in desert areas. So what I want to talk about is shown here in effectively 4 sections. I thought the first thing, for those of you who don't know much about desert environments, it would be useful just to briefly outline where they are and why they are where they are, and then really look at my research over last period of time, but looking very much at 2 aspects. First off, the importance of water in dryland landscapes. Something Dave didn't touch on though is also work that I've done on water and dryland societies. So it's a combination tonight of looking at some of the work I've done on the geomorphology of desert environments, but also some of the work looking at the more historical importance of water and dryland societies. And then I'll wrap up by giving you another brief movie clip showing some of my ongoing work. Now the lecture's colour-coded so that you'll know when we're getting towards the end. We start with an orange section, then we move into dark blue. When the green bits appear, you know that you're about halfway through. Then we'll go back to the orange again. There'll be a short film, and then you can applaud warmly at the end. Okay, so that's broadly how things are going to pan out. I think warm is probably quite an appropriate word actually when we start thinking about, I should say yes, this is using the full glory of the University of Brighton PowerPoint template in all its technicolor wonder. If we start off though just thinking about global deserts, where and why. And I should say before I start as well that I'm not really focusing on polar deserts, so I tend to prefer warm and dry environments as opposed to cold and dry environments. So I'm very much focusing on what we might refer to as the world's warm deserts or the world's hot deserts. Now, if you look at maps of the world, like this one produced by NASA that shows the Earth from space, you can straight away start to pick out whereabouts the world's drylands are. And you can see the belt that stretches through the northern hemisphere across from the deserts of North America that stretch up into Canada and down into Mexico. You can see the very large area of hyperaridity associated with the Sahara and then the Arabian deserts. You can see arid areas extending up into Central Asia, into China and into Mongolia, and then mirroring that but of a much smaller size, you've got the southern hemisphere deserts, the Atacama in Peru and Chile, the Kalahari and the Namib in southern Africa, and then the various deserts of Australia. That distribution is controlled by 4 sets of factors, and just to talk through some of these. The first of these is the fact that most of these deserts occur in areas of atmospheric stability. So they're in zones where either side of the equator where air is typically descending. They're associated with high pressure areas. And where you have areas of high pressure atmospheric conditions, air is typically descending rather than rising. Air that rises condenses and moisture can precipitate. These are areas where air is typically falling, associated with the downward limb of the Hadley atmospheric circulation cell. So these areas tend to be relatively dry. And that's why you get this belt north and south of the equator, because that's whereabouts these atmospheric zones tend to fall. But that's not the only reason why deserts are where they are. And you start looking at that pattern and you start to see complexities like when we look into Central Asia. The effects of continentality become important as well, whereby rain masses coming off ocean areas fail to penetrate into the interiors of large continents, hence the reason that the Central Asian deserts extend further north than the main belt of high pressure zones. Then there are some deserts that occur as a result of topographic effects. So you can hopefully see on there some of the American deserts. I'll talk in a moment about the Atacama that are in rain shadow zones in the lee of major mountain ranges. So the idea being that rainfall can't cross these topographic barriers. One side of the mountain range will be relatively wet, the other will experience a deficit of moisture. And then there are also some deserts which are affected by cold ocean currents, and these are normally upwelling cold ocean currents which lower water temperatures, and if you lower water temperatures you require more energy for evaporation, you get less evaporation, you get less rainfall. Now these factors don't operate in isolation. More often than not for any particular desert there may be a whole number of different factors that are important in terms of shaping why that dryland climate occurs where it does. And if we take the example of the Atacama that I've just enlarged there in South America, the reason the Atacama is where it is, and it's one of the world's oldest deserts, is really due to 3 factors acting in combination. First off, it's affected by a high pressure system, part of this high pressure belt that I mentioned a moment ago, the Pacific subtropical high. It's also affected by the Peru current or the Humboldt current, depending on who you read, which is a cold ocean current which goes up the west coast of South America, so it lowers ocean temperatures. And then also you've got the topographic effects of the Andes there, which prevent air masses from moving across from the Amazon basin and Argentina and getting across into Peru and Chile. So in the case of the Atacama, it's almost a triple whammy in terms of the effects that make this particular region arid. If you look at this map, this is a map produced as part of the Millennium Ecosystem Assessment. It shows more accurately the distribution of drylands. You can see much more clearly here. This is using definitions associated with the United Nations, broadly defining arid zones as being ones with an annual moisture deficit to varying degrees. You can see that same extent, but you can also see really the extent of drylands in places like Canada, which quite often we don't associate with being a relatively dry place, and also how far north into Russia and parts of the former Soviet Union those dryland areas extend in the northern hemisphere. What this figure also shows is it shows the distribution of drylands quite nicely down at the bottom there. And the figure shown there is suggesting that drylands comprise 41% of the Earth's surface. So actually, we tend to think of deserts as being reasonably small areas of the world. Actually, it's more than 40% of the Earth's land surface are technically experiencing moisture deficits. The other thing we tend to overlook is that actually these areas are often quite densely populated, or certainly quite heavily populated. And this figure, the figure here shows population figures dating back to the year 2000, where drylands were home to about just under 35% of the world's population. So that's getting on for 2.5 billion people living in areas of moisture deficit. Now, if we look at, again, looking in this case at population densities, just as a final sort of point why it's interesting studying drylands and why it's quite important to study them, you can start to see that actually there are certain parts of the world where densities of population are much higher than others. So you can see on this map generally fairly low population densities, but in places like India and China, through the Sahel, parts of North Africa, parts of Turkey and the Middle East, we have relatively high densities of people living in areas with low levels of moisture. And that includes some extremely large cities and urban agglomerations. I've put on this slide the locations of some of the major dryland cities with populations of more than 5 million. So places like Beijing, Delhi, Istanbul, Cairo, Karachi, Los Angeles are all in areas that experience, at the present day, moisture deficits. Now, fairly obviously, these populations need food, they need drinking water, so that requires an understanding of desert climates and how desert climates have varied over time and how that might affect moisture availability. And they also need, these areas are also major, particularly the cities are very, very major growth areas. They need access to building resources for construction. You may need to big infrastructure projects like big road networks, large pipelines transporting water and so on. And in order to do that kind of construction, we need a good understanding of what the nature of the desert ground surface is like. And that requires a better understanding of desert geomorphology so we can feed into civil engineering projects and so on. So all in all, there are some big challenges in desert areas, and I think that's really where my research fits in, is in terms of trying to, I guess, broadly further the understanding of climate in these areas, but also trying to understand the ground characteristics and the wider geomorphological characteristics of these particular regions. So that's broadly the context, I suppose, and why I do what I do. Now, what I do, as I said at the start, I can probably broadly split, we're into the blue section now. I can broadly split this into two main categories. The first one is looking at water and dryland landscapes, and the second is looking at water and dryland society. Now, Dave mentioned in the clip at the start about the importance of water as an erosive agent, and you can see from this slide from the Namib Desert in southern Africa, and also the couple of insert slides there from Australia and from southeast Spain, the importance of water in terms of shaping desert landscapes when it flows across the surface. And I'm not going to say any more about water on the surface, because there are people in the room who are way more qualified than I am to talk about water at the land surface. What I've been more interested in over my research career to date has been what happens when water sinks into the surface. So what goes on with that water that doesn't run off over the surface or evaporate? What happens when it gets below the ground and when it gets into channel sediments, for example, into those sorts of sediments you can see there in that slide? What goes on there? And that's really an area of research that's had much less work done on it compared to looking at surface water. So my overall research in this area really falls under the theme of looking at subsurface water as a geomorphic agent in dryland landscapes. In other words, what role does subsurface water have in terms of influencing desert landscapes? And I've focused on two main themes. One has been looking at what goes on once water goes beneath the surface and how it can form what are often known as geochemical crusts or geochemical sediments. Now, water soaking into the desert surface, into sediments and into soils, if it is carrying dissolved minerals or carrying compounds that can then be precipitated out beneath the surface can have quite a powerful control in terms of shaping landscapes by forming hardened crusts. And I've worked on a couple of materials called calcrete and silcrete in this context. More about that in a moment. The other area that I've worked on has been looking at these geochemical crusts as a source of information about past environments. So not just what do they do to landscapes, what control do they exert on surface features, but also what can we tell about past environments from them. And I've worked on three different materials here, calcrete again, silcrete again, and also currently working on a project looking at a material called aeolianite. Now, for those of you who are unfamiliar with these terms, I thought actually showing some pictures of them in the landscape might be useful. So here we've got a mixture of shots of calcrete and silcrete and aeolianite. So image B is a calcrete which is forming a cap rock in Morocco. So you can see straight away the control there, that the flat sort of shadowed surface there that you can see on top of this hill slope is capped by a more resistant crust that's formed from subsurface water, minerals being precipitated from subsurface water. This is a close-up, that's in Morocco. This is also in Morocco, diagram D, showing, in this case, cemented gravels. Images C and F are cemented dune sands, which are aeolianites. And I'll say more about these a little bit later on. C is from Oman, F is from the Atacama. And then photographs A, E and G. A is an example of silcrete coating landscapes in Australia. F is my colleague Stuart Ulliott in the Kalahari, looking at some silcretes this summer. G is probably one of our best examples of a silcrete outcrop in the UK. We have quite a lot of silcrete in Britain, or at least we did until people broke it to pieces and used it for building materials. The outer stones at Stonehenge are made of silcrete, as are the stone circle at Avebury as well, some of our very important archaeological monuments. Now, how these things form, I guess, because partly what I've been interested in is trying to understand how these different features develop. To illustrate this, you could spend literally sort of hours talking through this, but I just wanted to illustrate it with reference to calcretes. Now, calcretes are very important globally. They have been estimated by Dan Yalon, who's an Israeli geomorphologist, to underlie between 13 and 15% of the Earth's land surface. So you may have never heard of them, but actually they're incredibly important in dryland environments. And there are various ways in which they develop. And I've just shown here a couple of diagrams from the seminal study by Andrew Gowdy in the 1980s from his book Chemical Sediments and Geomorphology, showing two sets of ideas on how calcretes form. And actually the models are very, very applicable to other forms of geochemical crust. In essence, they form either by vertical transfers of dissolved minerals or by lateral transfers. So the diagrams on the left there show two sort of situations where you may get a crust developing. On the top one, you can see what's going on there is it's water being brought up to the surface by capillary rise. So evaporation is occurring, drawing water up to the surface, evaporating off the water, and the calcium carbonate is precipitated and left behind to form a crust. That's one possible mechanism. The bottom one shows almost the opposite situation, in this case where carbonate gets washed down from rainfall. It could be transported in as dust or as biological remains or from volcanic ash, all sorts of other carbonate sources, and then gets washed down through a profile where it precipitates out. So that's sort of processes that are typically found in soil environments. So these are broadly pedogenic processes. The alternative though, and this is I suppose where I've focused more of my work on, has been looking at crusts that form by lateral transfers. So there are very similar mechanisms involved here in terms there may be evaporation, there may be downward washing of carbonate, but in this case what you've got is water moving along, in this diagram, a valley, and cementing beneath the valley floor. So in the top part of the diagram you can see this sort of, in fact probably the bottom one's better, you can see this big lens of carbonate forming beneath the valley floor where water has flushed along the system, seeped into the ground surface and then cemented. And there are very similar models for explaining how silcretes form, and to a certain extent aeolianites develop as well. So that hopefully gives you a little bit of context as to how these things develop. Now what I want to do, and for both halves, I just want to give you three examples of work that I've been involved with, and some of it's past work, some of it's ongoing work. just to give you a feel for the kinds of information that we can get out of some of these different types of chemical crust. I'm going to start off by looking at, well, I've picked 3 examples that are really all around carbonates. So I'm not going to say much about silcretes at the moment, but one example on calcretes from Spain, one example on calcretes from Botswana, and then current work that I'm doing with a couple of members of the audience, I'll introduce them in a moment, on aeolianites in South America. And I guess the first example very much is looking at how calcretes can control landscape evolution. The second 2 examples are looking at what we can tell about past environments from looking at calcretes. So this first example is work that I've done with Roger Smith, who's out there somewhere, back in the 90s and early noughties. And it arises out of, we used to take students on field courses to southeast Spain. So it's a wonderful example of how teaching can feed into research and how we can actually get ideas from teaching and how it can trigger thoughts for research projects. We took students for many years to this particular part of southeast Spain, where there are some absolutely stunning landscapes which are fundamentally controlled by the presence of calcretes. And you can see hopefully here, so it's southeast Spain, it's an area here called the Tabernas Basin. It's between 2 mountain ranges that are in the southeast of Spain, and you can see in the top left diagram, diagram A there, how you can see the mountains in the background, but you can pick out this very, very pronounced flat plateau or paleo surface, which is supported by calcrete. So basically the only reason that that flat surface is there is because of the presence of a subsurface calcrete. Over here in photograph B, you can see the same features, but in this case it's on completely the other side of the basin. Some of these things are really very, very extensive. You can see the flat surface, and what you have here is bedrock overlain by a thickness of maybe 5 or 6 metres of alluvial fan gravels. So basically what's gone on, there have been water flowing across this landscape, smoothing off the bedrock, and then the whole lot has been buried by alluvial fans, so big spreads of waterborne sediments. The basal sections of those gravels have been cemented by carbonate to form what's called a groundwater calcrete. The upper parts have been cemented by soil forming processes to form a pedogenic calcrete, and what it's effectively done, it's almost like a double cap rock in this landscape, preventing erosion occurring. So the presence of these near surface crusts has actually acted to stabilise this landscape and limit the extent to which erosion can take place. You also see in the landscape, in the bottoms of valleys, much more recent things called channel calcretes, where the gravels in the bottom of river valleys are cemented by carbonate, and in this case they're controlling drainage evolution. They're forming waterfalls or nick points within the system and affecting the ability of the surface to be eroded. And this schematic diagram in the bottom right hand corner shows actually there are multiple examples of this in the landscape. So there are these sort of double layers of pedogenic and groundwater calcretes at least 2 levels. There are channel calcretes at various locations exerting a powerful control on the landscape. Now, part of this work that we've done has been designed really to provide a bit more information, not just about the bigger landscape context, but also the micro scale characteristics of these features. And the reason we've been working on this is because these features also crop up in the geological record. They don't just appear at the land surface, they also are quite important features of sandstone units that formed in desert areas in the geological past. So you find calcretes in the old red sandstone, you find them in the Triassic rocks beneath the North Sea, you find them in various different contexts. And there has been, until recently, relatively little known. Lots has been known about pedogenic calcretes, but relatively little has been known about the characteristics at the micro scale of other types of calcretes. So I suppose part of our goal has been also to look at these features and look at these materials and see if we can pick out perhaps certain characteristics that make them more easily identifiable in the geological record. So just to show some, in this case, some thin sections, these are microscopic wafers cut through calcretes that allow you to look at them under the microscope. The top example is a pedogenic calcrete, brown, murky, fairly sort of non-distinct looking, very, very fine crystals because of the fact it's formed near the ground surface, mainly by evaporation with very, very little time for crystals to grow. Contrast that with groundwater calcrete in diagram B there, which has a much more crystalline structure. These large blobs are basically rock fragments. The material in here is the cement in between, which is very much more crystalline. It has a more sparry cement. So we've looked at these materials in thin section. We've also looked at them under the scanning electron microscope. This is becoming, looking really, really detailed views of what these features are like, to again try to understand how they form and what their main characteristics are. So in photograph A, this is from a channel calcrete that's probably about 2 meters thick. And these photographs just illustrate some of the variability, even through a 2 meter thick unit of material. So you can see here a large quartz fragment with coatings of very fine crystalline material, a large quartz fragment here in B with fine grain material around it. Quartz grain there with some larger crystals of carbonate present. But when you work your way down towards the bottom of the profile, we get these absolutely beautiful rhombic crystals of calcite, where water has sat around within these sediments and has cemented them, but it's had a lot more time to develop and has formed these very, very attractive crystalline structures. So what we can see is water's important, but actually how long water hangs around within these materials also has quite a major impact on what they look like, and potentially how we can identify them in the geological record. The second example comes from Southern Africa. Now this is actually where the opening film was shot. A much flatter environment, much less incision, much more geologically stable, and very, very little dissection of the landscape, so you can actually see through these sort of complex calcrete profiles that I've just talked, like the ones I've just talked about from Spain. So this was a project that I've undertaken with Sue McLaren, who's at Leicester University in Southern Africa, and we've been looking at, in this case, calcretes that form within valley sediments. Bit different to channel calcretes, in that channel calcretes typically cement the whole base of a channel, whereas calcretes in valleys tend to form almost like pods along the middle of the valley. They don't cement typically the whole valley. But this just shows some examples of the sorts of materials we've looked at. So photograph A is from a valley called the Takatswani, very much more typical view of Kalahari calcretes, where you can't see a lot other than white stuff sticking out in the bottom of a very indistinct valley floor. Photographs B and C are from the Okwa Valley, which is a 600-kilometre long fossil drainage network in Botswana. And in this case, we're fortunate, whereas in Spain we don't know how old those calcretes were. In this example, we've been able to radiocarbon date shell material with all of the problems of radiocarbon dating shells. But from this particular outcrop, we've dated mollusk shells, and we've been able to tell broadly how old these calcretes are. And these particular examples date back to just about 12,000 years or so ago. So they date back to just after the end of the last glacial, the last ice age, as we were going into a period of warming following the glaciation, leading into the present day warm conditions that we experience. Now we've used a similar suite of techniques to look at these particular sediments. I'm just going to show some of the electron microscope work though, because it shows quite nicely some of the differences. So we found virtually no evidence for the coarser crystalline materials within these calcretes. So even though they're forming within a valley setting in a wetting environment where you will have had flushes of water passing through the landscape, they're very, very fine crystalline materials. So photograph A there shows nice windblown quartz sand surrounded by very, very fine crystalline calcium carbonate. B there shows the carbonate coating those grains. C shows some patches of silica. Sometimes you have silica precipitated out amongst the carbonate, but very, very different to what we were finding in Spain. Interestingly, in this environment, and something we didn't pick up at all in certainly the groundwater calcretes in Spain, was evidence of biological activity. So biota can also play quite an important role in cementing and preserving these sediments. So here you can see in A some fungal filaments which have been coated with carbonate and preserved as little microscopic tubes. And then in B and C we can see a material called needle fibre calcite, which is again another organic deposit produced by microorganisms. Very, very distinctive evidence there of biological activity. Now from these, I said we were interested in looking at paleoenvironmental information, how these things formed. in this particular context. By looking at these micrographs, you can actually build up quite rapidly, in this case, a history of how these things developed. Because most of the biological activity occurs within pore spaces, so gaps within the calcrete, in between this very, very fine microcrystalline material. And what appears to have happened in this particular instance is that there's been presumably flushes of water coming along these valley systems, which have sunk into the ground. Presumably there's been evaporation occurring, which has led to the precipitation of very fine calcite. But then presumably the water table has dropped, almost certainly as a product of drying in this area, allowing pore spaces that are dry for fungi to live in and other biological activity to occur within. So by looking at the micro scale, we can build up broad pictures of what's going on at the macro scale and try to begin to understand what's going on in terms of landscape evolution. So calcretes, you can tell something about landscape history, but you can also use them as a more detailed environmental record of how climates have changed. Final example is current work that I'm undertaking with Joe Bullard and Mark Bateman, pictured there. Joe's from Loughborough, Mark's from Sheffield, and Claudio Latorre, who's from the Catholic University in Santiago in Chile. And in this case, we're not looking at calcretes, we're looking at this material called aeolianite, and we've been working near a place called Copiapo, and you may remember Copiapo from the Chilean miners' rescue. The San Jose mine is highlighted by that Chilean flag there. So we were about 70 kilometres southwest of Copiapo on the Pacific coast. And in this case, we were looking at something very, very different. This is effectively a large area of dune sediments piled up against a mountain range that have been preserved by calcium carbonate. So they're aeolianites, they're dune deposits that have been, basically their preservation potential has been enhanced by the presence of these carbonate cements. And you can see in photograph A, that's a composite of what the whole area looks like. About 80 to 100 metres thickness of aeolianite there, and you can see in the other photographs the dune bedding structures all preserved by carbonate. We've been looking at again, trying to unravel the paleo-environmental record from these sites. And to do this was quite a complicated task in that these are very complex sedimentary units. But what we did in the field was break down the outcrops into identifiable units that we could distinguish in the field. So I've shown on this figure here a view showing all the different units that we were able to identify. At this site, 8 in total. We then measured the dip of the beds. So these are effectively dune sediments, and by measuring the dip of the individual sedimentary units, it's possible to establish potentially paleo wind directions, which direction the wind was blowing from in the past. And this little table just shows some data from the different units, and it shows the dip of the beds in the first column. Probably the most useful one is the right-hand one, which shows which direction the wind was blowing from at various times in the past when those units were deposited. Now, at the present day, winds blow dominantly from the south, and you can see there that these units swing round. Some of them are southerly, some of them are westerly, some of them are easterly. So what we're preserving there is a record of very, very varying wind regime in this particular landscape. We've been able to date these sediments. This is something that I've not talked about so far, and I'm not going to say a lot in detail about this because you can talk to Mark Bateman over a glass of wine later on if you want to know more. But Mark has luminescence dated these sediments, so trying to establish the ages at which they were deposited. And just for some of the units here, the ages are shown here, and these are in thousands of years before present. So site 1, sediments are pretty much all dating to round about 100,000 years or so ago, which was quite surprising because what it's suggesting is that 80 metres of sediment was probably deposited in a relatively short space of time, implying that the wind was very, very variable in certainly a geologically short phase. We also looked at another site, site 2, a little bit further to the north, and worked on similar processes, looked at paleo winds again. In this case, you can see similar swings of wind direction going from some southerly, some more easterly, some more westerly. And also we've dated some of these units, and some of the ages, or certainly the age of unit 5 at the top there, corresponds with the information from site 1, so suggesting we've got an overlap between these different sites. The lower dates there suggest even earlier phases of sediment deposition, going back maybe 180,000 years. So what we're getting effectively is a preservation of sediments of particular ages, but also, very importantly, information about past wind variability. So again, this is an example where you can use, in this case, geochemical crusts as a means of trying to understand how past environmental changes have occurred. Now, what we're trying to do at the moment, we're still very much in the process of working on this, but we're trying to see how this sequence ties in with other environmental records. And particularly interesting is how it ties in with sea level fluctuations, because these dune sediments are very close to the coast and they're all carbonate, they're mainly shell material, which is almost certainly deflated from the Pacific. It's been blown on shore. And what's interesting about it, if you look at the lines at the bottom there, that shows the sea level curve for this part of the world. Sea levels go up and down as glaciers expand and contract. And what we appear to be picking up here is sand being deflated just after high sea level stands. So what you've effectively got is sediment being pushed up into the continental shelf, and then as sea levels have fallen, that sand being available and being blown on shore. So what we're trying to do is to build up a record of really how these aeolianites can give us a bigger picture in terms of past environments, and then we can try to link that into wider records. So that hopefully gives a flavour of some of the work that I've done on geochemical sediments. We'll now move into the green section, which is actually slightly more than halfway through, you'll be pleased to know, and look at water and dryland societies. Now, this is very, very different in terms of work, and it's something that I've been working in for about the last 10 or 12 years or so. And it's, again, taking rather a historical slant on water and dryland societies. So much of my work on calcretes and aeolianites and silcretes has been from a paleo-environmental perspective. This is also looking at, in this case, past water. And what I've been doing with a variety of different colleagues has been using various forms of evidence to try to reconstruct, in this case, historical climate variability in deserts. And I've worked looking at historical climate variability in various parts of southern Africa, also more recently looking at past extreme weather events and exploring the societal responses to these kinds of variations in climate. Now, I'm only really going to talk now about the first couple of points there, just to give you a flavour of some of the work that I've done. I suppose it goes without saying that water is absolutely fundamental in terms of human livelihoods in these kinds of regions. The issue that I've been working on really is the fact that we don't have very long records of how climate has varied in many parts of the world. I think we're very lucky in Britain, Europe, North America to have very good climate records going back several hundred years, certainly in the case of the UK. But I think probably ironically, the areas where we most need to know about variations in climate in the past, particularly the dryland areas, only have very, very short records of instrumental climate data. So what I've been trying to do is to extend records and try to look at past climatic variability. What many of these areas do have, they may lack in actual rainfall data, but what they're often blessed with are vast archives of old material that contain climatic information. And it's these sorts of materials that I've worked on. So you can see very, very different from my more geological work. This is just an example of one of the sorts of documents. It's from a place called Kuruman in South Africa, from a London Missionary Society mission station from 1888, and it's written by Roger Price, who was one of the missionaries there, and it's describing, in this case it's saying there are two ways in which the water of the Kuruman fountain could be raised so as to bring the level up to ground just below the Moffat Institution buildings. It's a letter describing, in this case, adaptations and the need for irrigation in a dryland environment. And there are collections of archives around the world with literally thousands, tens of thousands of letters of this type from which we can get information about past climates. And I'm going to give examples of three short examples of projects, again, that I've worked on that use these types of information. Two that are in the past, one that's very much ongoing. Again, first off, the first project I worked on was in the Kalahari in southern Africa, and it's work with Georgina Enfield, who's at Nottingham University. And in this case, we used predominantly missionary sources, written by famous missionaries who worked for the LMS, like Robert Moffat here, with his outrageous beard. And also down in the bottom right there, David Livingstone, as in Dr. Livingstone, I presume, who was, before becoming a world famous explorer, a missionary who worked for the London Missionary Society. And the materials of the LMS were big in southern Africa, and they were mainly working in the central part of southern Africa. Their materials are all archived in University of London archives at SOAS, the School of Oriental and African Studies. And there are literally, literally thousands of documents held there. There's correspondence, there are journals, there are personal collections of papers. We had the privilege of reading David Livingstone's original papers, which were absolutely phenomenal. He had a very good dry sense of humour as well, actually, as well as being a very dedicated amateur scientist and explorer. Various reports as well. And what we did with these was read them, which was extremely laborious. But you can get information in this particular part of the world from a range of different locations. So missionary activity started in the south of the area, spread up through the edge of the Kalahari. Very few people lived in the main sort of heart of the Kalahari here in Botswana, but people lived along the margins. And where there were people, there were missionaries, and those missionaries wrote about their day-to-day lives. And by reading these documents, we were able to build up a record of how climate had varied. So what we did was we read documents year by year for different places and attempted to assemble on an annual basis what people were saying about climate. So it isn't necessarily very quantitative, but we were able to pick out things like major drought episodes, shown here in red. And this matrix shows the towns and villages that we have information for, and then from 1815 to 1900, what conditions were like. So drought episodes, which come out very strongly, are in red. Flood episodes, wetter years, come out in blue, and then there are various degrees of colour in between for relatively wet and relatively dry years. And what we can build from this particular record is evidence of drought episodes and also wetter periods. So we can pick out, highlighted here, 6 fairly prolonged drought episodes that affected this particular part of southern Africa. There's a degree of cyclicity to this as well, but we're also able to pick out, interspersed with those dry periods, wetter phases as well. So even though this is a desert area, or certainly a semi-arid area, there are periods when conditions are wetter than average. Now, to give a feel for what sort of things people were saying about this, and this is often some of the more interesting stuff, what people were saying about these regions, just gives a couple of quotes here. You know, this is Reverend Thompson in a town called Kanye, from a drought in 1884 to 1886. There's been a universal drought of great severity. I've had a pretty fair experience of what an African drought means, with the thermometer at 102 degrees in the shade. Reverend Lloyd in the middle there, twice this week I've been compelled to take my dinner without water. The drought is really serious. Quite what the villagers he was working with were going through, I don't know, but obviously for the missionaries here, this was pretty tough stuff. But then they report the breakup of the drought, and we've now had abundant rains. Second one here is from a wet period. In this case, it was following a drought in 1888. The drought's now broken up since the 4th of January. Splendid rains have fallen, all wonderfully Victorian. The middle quote there talking about Vryburg becoming a quagmire. This was a wet period that occurred right across southern Africa and is picked up in a whole number of different regions. People who've lived in the country for many years, so they've never known a season to be as this. So it's possible to use these kinds of records to build up quite detailed patterns of climate variability. And what we can do with these is compare our record, which is shown in grey over here, with instrumental data. So there are some parts of the Kalahari that did start to get rainfall data from about the 1880s. And that's shown with the black line here. And what this diagram, this is work very much in prep with Raphael Neukomm, who's at the University of Bern in Switzerland. What we're doing is taking the instrumental record and then correlating it against the actual, our values that we get for rainfall variability, degrading that record statistically, which produces the red bars there, and what they effectively represent is the instrumental record degraded to the same level of correlation as our rainfall variables. And what you can hopefully pick out here is actually, certainly during the 19th century, there's an awful lot more dry than there is relatively wet years. And what it appears to show is that there may be a drying trend throughout the 19th century. So it's possible to build up pictures of longer term climatic change as well. We've done similar work in Lesotho, the second example I want to talk about. In this case, it's with Stefan Graf, who's from the University of the Witwatersrand in Johannesburg, applying very, very similar methods. In this case, though, not just looking at missionary work, but also other colonial records, and expanding our language base from English into French. These are groups of missionaries working for the Paris Evangelical Missionary Society in Lesotho, and I always love this photograph because I wonder exactly what's happened to Reverend Martzolf on the front row's right hand, and exactly what Father Christella is doing under his hat. But the good thing about this is that these people, just like the Brits, were obsessed with the weather and wrote enormous amounts about it, possibly even more than we got from the Kalahari. So we've been able for Lesotho to build up a similar record of climatic variability using very similar approaches, which I show here simplistically. Again, in this case, almost like a bar graph showing wetter and drier episodes. And again, we pick out a number of droughts, some of them overlapping with the Kalahari. This one in the 1860s in particular was very, very widely felt across southern Africa. The wet phase in 1890-91 mirrors exactly what we found in the Kalahari earlier on. And it's possible to now start to look at wetter periods as well, see how they correlate. And then now build up bigger records across the subcontinent and do some regional comparisons. So we're sort of getting to a position where now we have records. You can see there as well why I'm really pleased I worked with Stefan Grab, because I now have a paper by Nash and Grab on my CV. But what we have now are bigger records. So we've got records from the Kalahari, we've got records from Lesotho, and we can add those to other records that cover the 19th century, from tree rings from Zimbabwe. So this is a record that by Matt Therrell and colleagues who tried to reconstruct rainfall variability using tree rings. Documentary records similar to ours from southern part of South Africa down here, and also records from caves picking out variability. And what you can begin to see when you start to look at these variables, and I apologise, I think probably the yellow is slightly faint there, but oh no, it's not too bad on the screen. What we can start to build up is a record of regional climate patterns. So you can see here at the bottom, these are all the various documentary records. So there's our Kalahari record, our Lesotho record, other documentary records. And what I've highlighted in yellow here are the common drought episodes. And you can start to see that there are some real distinct regional patterns in terms of droughts that we can pick out using these kinds of approaches. And they match quite well, very well, in fact, with the tree ring record at the top, where you spot the dips in the tree ring record. Some of the very dry episodes where you've got these lower values coincide really well. And what was beautiful about this, actually, this was published completely independently without us knowing, was that they pick out the 1860s as some of the driest periods in their record. And that's exactly coinciding with the documentary sources. So these are very useful sources and tie up very well with other types of paleo-environmental information, and can be used basically to extend rainfall records back into the past, at least qualitatively. The final example, you'll be pleased to know, comes from work that I'm doing at the moment, which is funded by the Leverhulme Trust. Those previous examples were both funded by the British Academy in a series of 3 grants from the BA. We're working at the moment on a project funded by the Leverhulme Trust, attempting to expand this work on climate reconstruction to other regions of southern Africa, and we're looking at Madagascar, at Malawi, and also at KwaZulu-Natal in South Africa. And at the moment we're very much in the process of working on the Madagascar materials, and it's work with, again, with Georgina Enfield, with Kathleen Pribble, who's a research fellow here at Brighton, Dominic Kniveton, who's at University of Sussex, and Jürgen Klein, who's at Haymark University College in Norway. And we're very fortunate again in Madagascar to have and the southern part of Madagascar is technically a dryland, the northern part gets slightly wetter, so I'm playing slight artistic license here with my drylands. But we're fortunate again that Madagascar also had a very, very big missionary presence. In this case, British, French, German and also Norwegian missionaries. The Norwegians were very big in Madagascar in the 19th century. Very little colonial influence because Madagascar only became a colony of France in 1895, but there were still visitors to Madagascar visiting the royal family and recording information about climatic conditions. Now in this particular study we're looking at rainfall reconstruction, but I just wanted to talk a little bit about something I suppose a bit different that we're able to do with these documents, which is to look in this case at extreme climates. So people talk about rainfall, they talk about drought episodes, but very importantly in this part of the world they talk about cyclones and hurricanes. And what it's possible to do is build up records of individual cyclone events and examine the impacts that they had on individual communities. So what we're currently producing are cyclone maps for individual years, going back through actually a large part of the latter, I suppose the second half of the 19th century, and extending it possibly into the earlier part of the 19th century. And the quote there, okay, rather a long one, but it gives you an idea of the sorts of things you get people talking about. This is a missionary, Chiswell, who worked for the Society for the Propagation of the Gospel, whose archives are at Oxford University. And he's describing here a severe hurricane passed near the town, destroyed our church and printing house. The Roman Catholic Church, a much larger one than ours, only put up 4 years ago, is as complete a wreck as our own. And then describing churches being blown to atoms by the wind. The only ship at Tamatave, which was one of the major ports, is wrecked. And very, very vivid descriptions. And we get very, 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 very detailed descriptions of this particular cyclone from a whole number of different locations. And on this map, I've colour-coded different impacts. So there's cyclones with the swirly symbol, red indicating destruction of features, blue indicating damage. So there were churches, there were colonial buildings, there were indigenous dwellings destroyed, there were deaths reported, there were trees and crops damaged. There was flooding in some places. You can get an idea of the extent of the damage by reading these documents. You can also tentatively begin to map where the cyclone path was from this by looking at the dates of documents and almost the sequence of damage done by individual events. And we know that this cyclone passed right along the coast. And we know that it didn't go that far inland because in Antananarivo, the very top left-hand of that diagram, they only reported strong winds rather than a hurricane. So it's possible to build up quite detailed records. And what we can do from this, we can look at maps that are produced of storms by, in this case it's NOAA, which is the National Oceanographic and Atmospheric Administration in the States. They produce tentative maps of historical storm tracks. And we can tell from that it was probably that storm there that affected this particular area in 1872. Another example here, this was an even more devastating one where you had widespread carnage right across. It's a little bit gruesome, some of this work, in terms of reading these. You get very excited when you read accounts of major destruction. But here you can see the extent of damage, where in this case there's 9 churches that have been damaged, 7 destroyed down in Mahanoro. Very, very detailed pictures, shipwrecks. There were accounts over in Manombo of cattle being washed out to sea, buildings being destroyed, people being decapitated by falling roof and masonry, all quite unpleasant things going on. But in this case, what appears to happen is that this particular cyclone crossed the island and then it tracked back on itself, which is actually quite unusual. Very tentatively, we can put that kind of curve for the pathway in. Now, what we're working on, and again, these match with one of the curves, it's probably this event here, shown by NOAA. What we're able to do from these records and what we're working on at the moment is trying to understand the severity of the storms, because there's current interest in cyclone intensity in the context of climatic change, and there are concerns about whether cyclone frequency will increase under climatic change or whether cyclone intensity might increase. And this work really adds some of the first information for the Southwest Indian Ocean that can feed into some of those climate change debates. On to the final orange section. What I wanted to finish with is another short clip that just illustrates some of the work that I'm doing at the moment in Southern Africa, and it's work that was carried out this summer, funded by the university and by the Research Challenges Award. So it's, I suppose, partly a way of saying thank you for that. What we're doing is, and it's just about 3 minutes or so. So what I've tried to do, and there's no sound on this one, thankfully. What I've tried to do so far, I guess, is to give you an overview of the work that I've undertaken in various drylands. But this is a little mini documentary almost of work that I'm doing at the moment. It's working on a very different material. It's working on silkrete, which I haven't said a great deal about, but it's a material that's very, very hard silica cemented sediment, very much like flint actually, and it's very widely used in stone tool making in Southern Africa and also in parts of Australia. The work's a collaboration between Stuart Ulliott, seen here, my colleague from the School of Environment and Technology, Sheila Coulson, who's an archaeologist from the University of Oslo, who specialises in the Middle Stone Age in Southern Africa. Her postgraduate student, Siggy Stowset, who's working on lithic technologies in Southern Africa from the Middle Stone Age as well, and also Mazawa Babutsi, who's a geologist who works at the University of Botswana, sorry, at the Botswana National Museum. We've been working in the area around the Sedilo Hills, which is where those opening clip was filmed, which is a UNESCO World Heritage Site. And there are a number of cave sites in that area that have been excavated and show that people have been living in this area at least since the Middle Stone Age. And most of the tools in the area are made of silkrete. The interesting thing, though, in this area is that there isn't any silkrete for at least 100 kilometres around these hills. So people are obviously selecting silkrete as a good material to make tools with and then transporting it to this particular location. What we're working on is a project that aims to use geochemical techniques to try to identify the sources of silkrete that are used in tool making. So we started off this summer working at the Botswana National Museum, where collections of artefacts are stored from Sedilo Hills. And this was quite important because what we needed to do was to first of all see if there were different types of silkrete that were being used in the field, and for tool making. So from Gaborone, where the Botswana National Museum is, we headed off to Maun in northwest Botswana, did our stocking up, bought our supplies, headed out into the field. And we're fortunate that the locations of where silkretes occur are quite well known. So they're in dry valleys, they're in pans, they're around the Okavango River. So these were the areas that we based most of our work. We spent just over 2 weeks in the field searching for silkrete outcrops. Stuart did a lot of the hammering, I did a lot of pointing, and described sites, logged them, sampled them. We covered about 3,500 kilometres in total, and sampled at 45 different sites. Things went pretty smoothly, apart from being trapped by a large bushfire and quite extensive flooding that prevented access to some of the sites. We've now sent the samples away for analysis, and I can't show you results at this stage, but we're very much eagerly awaiting the results, because if we're actually able to identify characteristics of silkretes that we can then match against sites, samples from these archaeological sites, potentially we've got the first ever evidence of, or the earliest evidence of prior planning in human society, in very, very early modern humans. I'd love to tell you more, but as I say, we don't have the results yet, and that'll have to be the subject of another lecture. So I shall leave the vehicles driving off into the dust and say thank you very much for your attention, and thank you for coming along, and thank you to Trevor for the film clips in particular. Thank you very much, everyone.